Good afternoon, everyone. So we are going to continue with our journey of Bayes' theorem. So Bayes' theorem, you do remember the formula, Bayes' theorem. Which is probability of A, event A, given that event B has already happened, is probability of A times the probability of B, given that A has happened, all of it divided by the probability of event B. This is the Bayes' theorem. It has a lot of applications where certain conditions are known. Something is given, you want to find out something. There are situations where you have scenarios where you know probability of B given A, but you want to find out the probability of A given B. Okay. So, for instance, you want to find out probability that somebody has a disease given that the person tested for that particular disease. Okay, tested positive for that particular disease. So the given condition is that somebody tested positive for something, and the thing that you are trying to find is that what is the probability that the person actually has the disease given that that test came out to be positive. So that's a very simple example. Then we talked about probability of an email being a spam given presence of certain words. So probability of an email being a spam mail given that certain words like dollar, sale, promotion, etc. being present in the email. So some things are given, some things you know, but there is something that you don't know. Given those things, what are the chances that the unknown will happen, or what is the probability that some other event will happen? So let's continue with our sales, traveling salesman example. We talked about it last time. I kind of want to refresh your memory on this, and I'll go ahead and do the problem again, and then we'll continue with more examples of Bayes' theorem. All right. So in the traveling salesman problem, the person stays at hotels A, B, and C. 50% of the times he stays at hotel A. 30% of the times he stays at hotel B, and 20% of the times he stays at hotel C. And when he arrives at hotel A, 5% of the times there is problem with reservation. When he arrives at hotel B, 10% of the times there is problem with reservation. And similarly for hotel C, 15% of the times there is reservation problem. And these together collectively we call R reservation problem, okay? Problems with reservation. A is the event that the person stays at hotel A, B is the event that the person stays at hotel B, and C is the event that the person stays at hotel C. Now, the first question asks you, what is the probability that the person stays at hotel A and has reservation problem? So in essence, the question that is being asked is probability of A and R. That means stays at hotel A and has reservation problem. Okay. So there's going to be probability of staying at hotel A times the probability of having reservation problem given that the person stays at hotel A. All right. So probability of staying at hotel A is 50% because 50% of the times he stays there times the probability of having reservation problem given, so this is given that the person stays at hotel A, that means you are restricted to column A. So in that case, the probability of having problems with reservation is 0.05, that is going to give you 0.025 or 2.5% chance. In the next part, the problem asks you, what is the probability of, in general, having a reservation problem? What is the probability of, in general, having a reservation problem? Okay, so that is something that you need to think a little bit. When can you have reservation problem? Okay, when can you have reservation problem? You can have reservation problem if you stay at hotel A. You can have reservation problem if you stay at hotel B. You can have reservation problem if you stay at hotel C. These are the only three possible ways you could have reservation problem, which in essence tells you the total probability of reservation issue or reservation problem is going to be sum of these individual probabilities, which is to say probability of R is the same as the probability of staying at hotel A and having reservation problem plus probability of staying at hotel B and having reservation problem plus probability of staying at hotel C and having reservation problem. If you add this up, you'll get the total reservation problem. The first one, by the way, we got it, which is 0.025 probability of staying at hotel A and having reservation problem. Now let's do the similar calculations for hotel B and hotel C. So probability of staying at hotel B and having reservation problem is going to be probability of staying at hotel B times the probability of having reservation problem given that the person stays at hotel B. And note, probability of staying at hotel B is 30% or 0.30 times the probability of reservation problem or reservation issue given that the person stays at hotel B. Given means it restricts you to this column B. So if you stay at hotel B, what is the reservation problem chance? That's 10%, which is going to give you 0.03. Okay. Similarly, probability of staying at hotel C and having reservation problem is probability of C times the probability of having reservation problem given that he stays at hotel C. 20% of the times the person stays at hotel C, and times probability of reservation issue given that the person stays at hotel C means you are restricted to column C is 15% or 0.15, which is going to give you 0.03. So this number is 0.03, this number is 0.03, and I add all these numbers to get the total reservation problem, which is 0.085, I believe. Yes. So the total reservation problem is 0.085. Now, let's go ahead and find the conditional probabilities. So what are the chances that the person is going to stay at hotel A given that there was a reservation problem? That's part 3. So let's use a different color. So part 3, what is the probability that the person is going to stay at hotel A given that there is problem with reservation? Okay, there will be a problem with reservation. So in that case, is going to be probability of A times the probability of R given A, all of it divided by the probability of having reservation. This is nothing but Bayes' theorem, okay? Instead of B, I used R. Okay. That's the only difference. Now, probability of reservation problem, which is 0.08, so 0.085, and then probability of staying at hotel A is 50% or 0.5 times probability of having reservation problem given that the person stays at hotel A is 0.05, which is 0.025, all of it divided by 0.085, which is 25 over 85. I multiply both sides by, both top and the bottom, or the numerator and the denominator by 1000. That gives me this number. 5 goes into 25 5 times, and 5 goes into 85, I think 17 times. So 5 over 17. And if you do the math, so 5 over 17, 5 divided by 17 comes out to 29.41. So approximately, I'll use approximation, 0.2941, which is approximately 29.41% chance. There is about 29.41% chance that the person will stay at hotel A, given that there is a reservation problem. Remember, this reservation problem is not with hotel A. It's a general reservation problem. In general, if there is a reservation problem, what are the chances that the person will stay at hotel A? Similarly, we could do probability of staying at hotel B, given that there is a general reservation problem. So it's going to be probability of B times the probability of B given A, all of it divided by probability of B. Now I just plug in these numbers. Probability of staying at hotel B is 30% times probability of having reservation problem at hotel B is 10% or 0.10 or 0.1. All of it divided by 0.085. That's going to give me 0.03 divided by 0.085. I'm just going to put a 0 here so that I can align that digits after decimal. If you multiply the numerator and the denominator by 1000, you're going to get 30 over 85. 5 goes into 36 times, 5 goes into 85 17 times. So this is going to give you 6 over 17, which is approximately, I think, 35%. 6 over 17 is 0.3529. 0.3529, that's equal to 35.29%. So there is about 35% chance that the person will stay at hotel B, given that there was a reservation problem. Similarly, what is the probability that the person will stay at hotel C, given that there is a reservation problem? It's the same thing. Probability of staying at hotel C times the probability of having reservation, given that the person stays at hotel C, all of it divided by probability of a reservation. Reservation issue. Probability of having reservation issue is 0.085. Probability of staying at hotel C is 0.2 or 20% times probability of having a problem at hotel C is 15% or 0.15. There is going to be 0.03, and then I put a 0 to align it, 0.085. That's going to be equal to 30 over 85. That's going to be 6 over 17 again, which is approximately 0.3529. That is equal to 35.29% approximately. So given that there is a reservation problem, there is a 29% chance, okay? There is about 29% chance that the person would stay in hotel A. There is about 35% chance that the person would stay at hotel B, and there is 35% chance that the person would stay at hotel C. And that is how you use Bayes' theorem to find conditional probability, given that some other conditional probability is known. In this particular case, we know something, probability of reservation problem, given that the person stays at a hotel A or B, or I think I just made a slight typo. People didn't notice it. Probability of B, this should be probability of R given B. Why did the A come from? Okay, so, all right, any questions, anybody?
No, I don't have any at the moment. Thank you.
Okay,
No.
is the problem clear?
Yes.
I have a question.
Yes.
So, for example, how you put P and then the parentheses R and then A, does it matter like which way they go? Like, does it matter if you put R before the A or the A before the R? Does that matter?
Of course, of course.
Okay.
So if you put probability of R given A, that tells you, remember, whatever is to the right of vertical line that's given to you, that's 100% true. So probability of having a reservation problem, given that the person stays at hotel A. On the other hand, if you write probability of A given R, this one says probability of staying at hotel A, given that there was a reservation problem. So it's completely opposite.
Okay. Thank you.
Next, anything else, anybody? Okay. So, breast cancer problem. This problem is kind of very kind of compact in wording that could be a little bit harder to read, but let me break it down for you. A mammogram is 90% accurate in correctly predicting breast cancer in women, okay, in a woman. That means true positive. So you test for breast cancer 90% of the times. If the result is positive, the person has cancer. But 10% of the times, even though the result is positive, the person does not have cancer. And the second statement after this end, 15% inaccurate in predicting it. 15% inaccurate in predicting it. That means 15% of the times when someone has breast cancer, the test will, 15% of the times, the test will be inaccurate or giving negative results, even though the person has breast cancer. That's what it is. Okay, so it's a bit tricky to follow this thing. So what do they want? In the general population, about 1% of the women between the ages of 40 and 50 have breast cancer. If a woman tests positive, then what is the probability that she has cancer? All right, so let's go ahead and kind of create a mini diagram for you. Let me use black here. So please pay attention to this diagram. This is gonna help you understand things. So there are 4 quadrants here. C is the event that someone has cancer. And C prime is the event that someone does not have cancer. Remember, complement? And this is positive, means someone tests positive. This is negative, means someone tests negative for cancer. So this is the diagram. It really helps you see things. Okay. Now look, the person tests positive and has cancer. That means true positive, meaning 90% of the times is good. Okay, test positive and actually has cancer. But 10% of the time, the person tests positive, but actually does not have cancer. So this is 0.10. On the other hand, 15% of the times, the person tests negative, yet the person has cancer. So that would be 0.15 right here. 15% of the times you tested negative, but you do have cancer. On the other hand, 100 minus 15 or 0.85% of the times you test negative and you do not have the cancer. You test negative and you do not have the cancer. That's what it is. That's what the problem is. Now, what the problem is asking is this. What is the probability that someone has cancer, that means C, probability of event C being true, given that someone tests positive for the cancer? This is like a very basic common question. Like somebody goes to a doctor and doctor does a test on you and says you have this disease. Now, given that the test came out positive for that disease, do you have the disease? That's a question everybody asks. So in essence, if we format the question in math term or in statistics/probability term, it is like asking the question, what is the probability of having cancer, or what is the probability of having that particular disease, given that, so this is vertical line, given that you already have tested positive for that disease, or in this particular case, what is the probability of having cancer, given that you have already tested positive for cancer? Now, this is a straightforward application of Bayes' theorem. So what this is going to be equal to probability of having cancer times the probability of testing positive, given that the person has cancer, all of it divided by the probability of testing positive. All right. Now, let's go ahead and work on this problem. We're going to find all of these things one by one, probability of cancer. So now in the general population, probability of having cancer is 1% or 0.01. Then the probability of not having cancer is 100 minus 1 or 99% or 0.99. So chance of having cancer is 1%, chance of not having cancer is 99%. This is the straightforward diagram, but sometimes there is a tree diagram that people draw and some people like it. So I'm going to try to draw it. So let's say you start here, an individual, okay, a human being. You can see my artistic skills.
He looks like he has dreadlocks.
Okay.
He's
It's
a
she.
Rastafari.
Rastafari. It's supposed to be a she. You can see my artistic skills. I'm definitely not gonna compete in any art competition for sure. All right. So how can I make it look more like a woman? Okay.
Draw a dress on it.
Draw a dress on it. I don't know. Okay. So, all right. This is hilarious. Okay.
She has chicken feet.
She has chicken feet. Okay. I need to make it bigger. Okay. So, you know what? There was something I learned while working on these problems and this particular cancer problem. And there is, men can also have breast cancer. I didn't know that. It's not only women who can have breast cancer, even though it's rare, but it does happen to men too. Men can have breast cancer too. Interesting, I didn't know that. So there are two scenarios. You either have cancer, right? Or you do not have cancer, that's C prime. C prime is the C complement. Then if you have cancer, there are two things could happen. You could test positive, right? Or you could test what? Negative. Similarly, if you do not have cancer, you could test negative or you could test positive. So probability of having cancer is 0.01, right? If you have cancer, the probability of testing negative is 90%, positive is 90%, and probability of testing negative is 10%. If you, this is minus, all right? So let me erase it and then kind of make it further away. Okay. Oh no, this is not minus, this is positive, sorry. Okay, so the probability of not having cancer is 99%, 100 minus 1.99. If you don't have cancer, you still test positive is 15% or 0.15. And when you do not have cancer, you test negative, and that is 100 minus 15 or 0.85 or 85%. So this is a diagram that some people use too, but whatever clicks with you, go for it. I'm okay with either. Main concept, main thing here is to make sure that you understand it. So let's find out these things. Probability of having cancer. So I'm gonna find the terms in the numerator and find the term in the denominator. So probability of having cancer is easy, which is probability of having cancer is 1% or 0.01. Now the probability of testing positive, given that one has cancer, so probability of testing positive, given that one has cancer, so you have one has cancer and test positive, that's 90% times 90%, right? Given that you have cancer, so 0.9. Now, probability of testing positive, the denominator, probability of testing positive. Now look, how can you test positive? So look at this diagram. You could test positive here, right? And you could test positive here. Is that clear? The other two results are negative. So if you test positive here, in the first case, which is this one, probability of having cancer and testing positive. That's one scenario. This is the first one. And the second one is this one, probability plus probability of not having cancer. Okay, probability of not having cancer, because to get to this point, you must not have cancer, and then you must test positive. That means, and you test positive. Or in another way, you can say the same thing. You can test positive. So let's look at the other diagram. If this one works for you, fine. If this one doesn't work for you, that's fine too. From this diagram, testing positive. How can you test positive? You can test positive when you have cancer. That means you're in C column. You can test positive when you do not have cancer. You're in C prime column. So that's 0.1 or 10%. So these are the things that you need to be careful about. Now, probability of testing positive equal to probability of cancer and testing positive. So there's going to be probability of having cancer times the probability of testing positive given that the person has cancer. There's this term. Plus this term, probability of C prime times the probability of testing positive given that the person does not have cancer. Now I just plug in these values. This is pretty easy. Probability of cancer is 0.01 plus probability of testing positive given that, not plus, sorry, I meant times the probability of testing positive given that the person has cancer, which is what, 90%. Testing positive given that you have cancer, that rest given C restricts you to the first column. So it's 0.9 plus probability of testing, probability of C prime, which is, by the way, the probability of C prime is 99% or 0.99 times the probability of testing positive given that you do not have cancer, which is 0.1. And if you simplify these numbers, it's going to be 0.009 plus 0.099, which is going to be 0.108 or about 10.8% chance. So probability of testing positive is about 10.8% or 0.108. Now we can go ahead and do this problem, which is going to be this probability of cancer, given that the person tests positive, is going to be in the denominator, probability of having cancer, which is 0.108, and on the top, probability of having cancer is 0.01 times the probability of testing positive, given that the person has cancer, is 0.9. That's going to give you 0.009 over 0.108, which is the same as 9 over 108. And that is, I think, approximately 9 divided by 108. Oops. 9 divided by 108 is roughly about 0.083. 0.083, or about 8% chance that the person has cancer. There is about 8% chance that the person has cancer. All right. Is this clear to everybody?
It's still confusing to me.
It's
Yeah,
still,
Okay.
so confusing.
Yeah, if it is confusing, that's normal. Because I have been doing this problem for many years, and still sometimes nowadays I don't look at it. But in my first few years when I was teaching this problem, I had to look it multiple times. And then when I would try to do it in the class, I'd still make mistakes. It happens. So if you are struggling with the idea, that's not unusual. But the main thing is to take your time, look at it, and go back and look at it, go back and look at it. This is one of the problems that you may have to look 3, 4, 5 times before you start to get a feel for it. And that is why I'm recording these sessions, so that you can go back and look at these recordings, okay? So any particular part of this problem that you don't follow, I know is a bit difficult to follow since you're seeing it for the first time, but anything major that you did not follow that I could touch on here?
You lost me at when you first started making the diagram, and then you came up where you put 0.01 and 0.99. I got lost after that. I don't know how you got that. So
Okay, let me try to break it down for you. I'm happy to spend more time on this problem. This theorem didn't get much attention by the Bayes theorem until recently, honestly, because it has a lot of application in artificial intelligence, machine learning. Reverend Bayes, sometimes in the past, I don't know, 150 or 200 years ago, whatever the time may be, he came up with this theorem, and it was there, but now its usage is a lot. Because I just gave you this. What is the probability? I'll give you some examples. Just think, everybody is getting mortgage nowadays. Not everybody. Everybody is getting loans, pretty much. Almost everybody is getting loans, and many people are getting mortgage loans. Did you know that mortgage loan has this Bayes theorem in a way? How? What is the probability that a person who is applying for mortgage will get approved, given that the person has 100K income, 760 credit score, then a stable job, and so and so. whatever it may be. Do you see? These are nothing but conditional probabilities. In loan application process is conditional probability. It could be a loan for homes, which is called mortgage. It could be auto loan. It could be loan for furnitures. It could be student loan. When they're giving you these loans, they're doing analysis. They're doing study on you. They're doing conditional analysis. It's very true. And when it comes to conditional analysis, Bayes' theorem is very useful. All right. Now, Don, to go back to your question, let me clarify this problem. Actually, this problem has poor wording. And even though I made the problem, I think I'm going to change it. Okay. There are two things that could happen. Okay. First thing is this: a person has cancer, means has cancer, does not have cancer. These are the two things that could happen, right? In broad scale. Has cancer and does not have cancer. When a person has cancer, there are two things that could happen. The person could test positive or the person could test negative, right? If the person tests positive and has cancer, that's actually called true positive. Okay. On the other hand, a person has cancer but tests negative, that's called false negative, because the person actually has it, but the result came out to be false. I mean, yeah, result came out to be negative, which is a false statement. Then, if the person does not have cancer, there are still two things could happen. The test could be positive, showing that it's a false positive, right? Or true negative, meaning the person does not have cancer and come out to be negative. So this is going to be true, false positive, and this is going to be true negative. Okay. Now, has cancer and test positive is 90% chance, or 0.9. This is the information that they give you. And this one, test negative, okay? Test negative, when the person has cancer, that comes out 15%. That's also given in the problem. Okay, so look, how does it work out? Has cancer, that means you're in this column, and test positive 90% of the times, good. Then again, has cancer, but you test negative, which is this one, 15% of the time. So that's what this one is. Similarly, when the person does not have cancer, the person could test positive. So in this row, which is 10% of the time. So there's going to be 0.10 or 10%. I'll rather stick to one convention, 10%. And the person does not have cancer, which is in the second column right here, right? And also test negative, that's 85% or 85% here. And that's how I created this diagram. So let me just do it for you here. This is all given. These percentages are given to you in the problem. Okay. So cancer, no cancer. Test positive, test negative. So has cancer, test positive, 90% or 0.9. Has cancer, test negative is 15%. Does not have cancer, test positive. Okay, does not have cancer, but test positive, 10%. Does not have cancer, test negative, which is correct, 0.85. And that's how I come up with this table. Now, where do I get the 0.01 or this number and this number? In the problem, they say that women between the ages of 40 and 50 has about 1% chance of having cancer. That's where this 0.01 comes from. If a woman has 1% chance of having cancer, what percent chance that she doesn't have cancer, which is 0.99% chance. And that is what it means. That's how you come up with this. Now, what we are trying to do, we are trying to find the probability of having cancer given that someone tests positive. And that would be probability of cancer times the probability of testing positive given that the person has cancer, all of it divided by probability of testing positive. And that is this formula. And I tried to find these values, and this value, and then plug it in. The top two are easy. Probability of having cancer is just 1%. Probability of testing positive given that someone has cancer, so which is this 0.9. So the top is going to be 0.01 times 0.9. Now divided by probability of testing positive. Now look, you can test positive when you have cancer. Look at the positive row. You can test positive and have cancer. And that means you take 0.01 and 0.9, multiply them, 0.01 times 0.9. Then you can test positive when you do not have cancer, okay? You do not have cancer, but you test positive. So, which is gonna be 0.99 times 0.1. If you do the math, it gives you 0.009 over 0.108, which is 9/108. That is about approximately 8% chance. That's how I did it, okay? Please do keep in mind, this is a little bit hard problem, okay? Conceptually, it's a bit hard to grasp at the beginning, but don't give up, okay? Don't give up. Just watch the video and come back, and if needed, I will explain it again.
My spouse is going to be working overtime with me on this stuff.
Okay. He may have to. If he hasn't done this problem for a while, he may have to actually do some thinking about it because it's not an easy problem. So just be patient, okay? Anybody else? Any questions? All right. Now, there is a second part to this problem and third part to this problem. And I'm so reluctant to erase all of this, but I don't have any more space. So let me just erase it for now. If I need it, I'll bring it back. In the second part, look, in the second star here, it says, find the probability that someone has breast cancer given that the person tested positive second time. Okay, not first time only, second time. So as a second opinion, you go to the doctor, go to a different doctor or to the same doctor, you can do a testing second time to see what is the probability that the person has cancer. Now this time, by the way, things are this. Again, we draw the same box. You test positive, you test negative. One has cancer, one doesn't have cancer, right? This time, what are the chances? So remember, this is a bit different. Probability of having cancer, given that the person not only tests positive once, which we found before, but the person tests positive twice. all right? Probability that the person tests positive twice. Now, this is where you need to think a bit. I have this thing where I kind of want the students to think about it before I give the answer away, because I had to think about it when I learned it for the first time. So what is it gonna be? I kind of want to find out from you what goes here and what goes here. What percentage of the new population has cancer and what percent does not? Any comment from anybody would be appreciated.
I have no idea.
Would it not be
Alright.
the same as the first one?
What is it, Monica?
Would it not be the same as the first one?
1%?
0.01 and 0.99?
Okay, good. At least a good try. Anybody else? Any other person want to comment?
Would it be 0.9 and 0.1 for the double positive?
I'm not quite following you, honestly.
If you can add them together, so for testing positive, 0.9 plus 0.1, the 0.10, the 10.
Okay, yeah, you're right there probably. That's an assumption we can make. But I'm asking, what is the value of C? What are the chances of C happening? That means, what is the probability that a person would have cancer?
Wait, would it double since they're testing it twice, or
Okay,
I think I'm confusing myself even more.
it's okay. Confusion is part of learning. Anybody else wants to pitch in? Nobody? All right. See, we are considering a group of people here who already have tested positive once, right? Because you cannot test second time unless you test positive the first time. That's kind of the assumption here. To be able to test positive second time, it has to be the case that you tested positive first time. Are you with me on that?
Yeah, so far.
So far. Now, the population of that tested positive, in the last problem we found, the probability of having cancer for the population that tested positive, that was what, 0.08 about, isn't it?
Yeah, it was 0.083.
So 0.083 or 0.08, let's say, for simplicity. So this is the population of people who tested positive. They are the ones who are going to go and test again or test second time. So in the new population, C is 0.08. And C prime is 100 minus 0.0, I mean 100% minus 0.08, or 100% minus 8% is 0.92 or 92%. That's the difference. Other than that, we can kind of make the assumption that testing facilities, is still kind of at the same level. It is accurate 90% of the times, inaccurate when people have cancer 10% of the times. And then it mispredicts cancer. I mean, says doesn't have cancer 15% of the times while people have it, and 85% of the times it does predict it correctly as negative. So that's the only difference. And so we could do the following. So there's going to be probability of cancer plus, not plus, sorry, times probability of testing positive twice, given that someone has cancer, all right? All of it divided by the probability of testing positive twice. This positive kind of is, you have to keep in mind, it's like testing positive second time. That's what it means. So now, what is the probability of cancer in the new population, which is, by the way, 0.08 times what is the probability that someone tests positive? We left that percentage kind of at 90.9 divided by testing positive twice. So think this is testing positive twice. This problem is a little bit complicated, as well as there are some assumptions that you could question, okay? So this is one of the assumptions someone could potentially question, but for the sake of argument, we are assuming that even in the second group, it's 90% accuracy. Second group means somebody who tested positive in this new population. So it's going to be 0.9 times 0.08. Okay. Probability of C and testing positive twice. Okay. Probability of having cancer and testing positive twice. Okay. Plus probability of not having cancer and testing positive twice. So these are the things. This is basically just this. So testing positive twice, and having cancer will be probability of cancer times the probability of testing positive twice, given that person has cancer. Similarly, probability of having no cancer times the probability of testing positive twice, given that the person has no cancer. And this is 0.08 times this is 0.9 plus C prime is 0.92 times 0.99. Not 0.99, sorry, 0.92. So plus point C prime. I just made a slight mistake. Sorry, my bad. This is probability of not having cancer is 0.92, right? This, and probability of testing positive twice, given that the person does not have cancer, is 0.1. So this should be 0.1. So 0.92 times 0.1. And if you do the calculation, how do you get that number for you? So 0.9 times 0.08 plus 0.92 times 0.1, there's going to be 0.164. And the top one is going to be 0.08 times 0.9 is 0.072. So probability of having cancer, given that the person tested positive twice, would be 72 over 164, right? So 72 divided by 164, that's about 43%. Approximately, I'd say approximately 44% chance. Okay. So that is what the situation here is. So second time around, if the person tests positive, is 44% chance that the person will have cancer. So last time, so I'm gonna put it here for your reference. The first time the probability was having cancer, if the person tested positive once, was about 8%. So probability of testing or having cancer, given that the person tested positive twice, is approximately, this is also approximately 44%. Now, I'm going to leave it up to you to do the same problem, but this time I want you to find the probability of having cancer given that the person tests positive, how many times? 3 times. And approximately, what is that number? I'll give you 3 minutes to work on it. Everybody go ahead and work on it. So this time, again, I'm going to create a diagram. Test positive, negative, has cancer, or the person doesn't have cancer, C prime. Everything is the same assumption wise, 0.1, 0.15, and 0.85. Only difference is that this time we are considering a population that has already tested positive twice. So that means there is a 44% chance that they have cancer, 0.44, and there's a 56% chance that they don't. So probability of having cancer, given that the person tests positive 3 times, is gonna be, so this is testing positive 3rd times, okay? So it's gonna be probability of having cancer times the probability of testing positive 3 times given cancer, then probability of testing positive 3 times. And the straightforward thing, the top probability of having cancer is 0.44 times the probability of testing positive when has cancer, 0.9. And in the bottom, probability of testing positive and having cancer, probability of testing positive and not having cancer, which is going to be easy, 0.44 times 0.9 times 0.9 plus 0.56 times 0.1. If you do this math, what do you get? Let's see, 0.44 times 0.9. 0.44 times 0.9 is 0.396. 0.396 divided by plus 0.56 times 0.1, that's 0.452. 0.452. 0.396 divided by 0.452 is about 87.6%, or approximately 88% chance. Okay, so someone who said 87.6%, so that's what the answer is. So this is about 88% chance that someone has cancer. Now, if I were to ask you, find the probability of someone having cancer, given that the person tested positive 4 times, you do the exact same thing, change this number to 0.88 and change this number to 100 minus 1 minus 0.88 is 0.12. And you can keep going it. As you can see, this percentage, the more tests you do, the better the chances, or the more the chances that the person has cancer. Because if a person is tested multiple times and it kept coming out positive and positive and positive, of course, it's probably cancer. This is just, by the way, one thing that you need to remember here. This is just for a random person that we picked off the street. All right. This example is not true. If the probability of having cancer, given that someone tests positive, is 8%, we should stop going to the doctor, because that's pretty low, right? That's very low. Then the doctors are inaccurate, or that those tests are inaccurate. So we can just rely on flipping a coin or something. So why is it that way? The assumption in this problem is that you randomly select one person from the population. So you randomly select a person walking on the street and pick him or her up and say, hey, let me check you for breast cancer. Or randomly pick a woman from the street and test her for breast cancer. In that case, there is an 8% chance. However, the reality is this: when you go to a doctor with certain symptoms, if a woman goes to a doctor with certain symptoms and doctor talks to the person and asks family history or symptoms or does some physical checking and everything, and then says that, okay, we may have to do a breast cancer diagnosis, let's go and order some tests and get the answer back. And if it is positive, then it's not going to be 8%. It's probably more like 90%, probably, I'd say, or something pretty high. Because that's not picking a random person from the street. That's picking a person by a specialist who does cancer screening or breast cancer screening for living. He or she is a specialist, okay? The person knows. So when the person says that, oh, okay, you're gonna go and do testing because I see all the symptoms that you may have breast cancer, then of course, the chances are much higher. Is it okay, guys? Plenty of time I spent on this problem.
Much clearer, thank you.
Thank you.
You're welcome. Let's move on to the next problem. Garments manufacturer. This is a problem exactly like traveling salesman problem. So in Bangladesh, a garment factory named Navy Hosiery makes socks at 3 different manufacturing plants named A, B, and C, with 50%, 30%, and 20% of the production coming from them, respectively. Also, A, B, and C have 1%, 2%, and 3% defect rates, respectively. As a quality control manager, you find an item defective. So you're a quality control manager, the shipment came in and you found a defective item. Okay, now you need to analyze and say, okay, who is the, or which plant is the most likely to have produced this defective item? Which plant is the most likely to have produced this item? So you can just guess it. We are expecting that you do some analysis and come up with a reasonably logical conclusion. So let's go ahead and do that. So again, plants A, B, and C, 50% production coming from A, 30% coming from B, and 20% coming from C. And there is 1% chance that A has faulty default rate, 2% and 3%. Let's define the events. A is the event that plant A makes the product. B is the event that plant B makes the product. C is the event that plant C makes the product. And D is the event that the product is defective. Okay, once again, A is the event that plant A makes the product, B is the event that plant B makes the product, and C is the event that plant C makes the product, and D is the event that the product is defective. Okay, now you as a manager, quality control manager, you found the product defective. So that means it is given. Given that the product is defective, what are the chances that A has made it? You need to find that. Given that the product is defective, what are the chances that plant B has made it? Given that the product is defective, what are the chances that plant C has made it? So these are the probabilities given something. Remember, Bayes' theorem deals with conditional probability where something is given. In this case, given that the product is defective, who may have made it? A made it, B made it, C made it. We find probabilities for each of these. So we find the probability of A making the defective product, similarly B making the defective product, and C making the defective product. Whoever has the highest probability is probably the plant or factory that made the product. So this is the overall setup. This is pretty much like a sales person problem, traveling salesperson problem. Now let's do one of them. Probability of A making the product, given there is defective, is gonna be probability of A times the probability of defective given A divided by the probability of defective. And similarly, you can do it for B and C. So let's just do one. Probability of A is 50%, right? Probability of A making it is 50%. So that's there. Probability of defective, given that A has made it, given that means you are restricted to A, so which is 1%. So this value is 0.5 and this value is 0.01. So I'll just go ahead and write it here. 0.5 times 0.01. Now we need to find the probability of defective. So that's the part that we need to calculate. Okay. So probability of defective. Now, if a product is defective, how could you get a defective product? Maybe it has been made by A, or it has been made by B, or it has been made by C, but you don't know which one. So you have to add up all the probabilities to get the total defectiveness probability. So probability of event A, probability of A and being defective, that means the defective product was made in A, probability that the defective product was made in B, which would be probability of B and defective, plus probability of C and defective. And probability of A and defective, probability of A and defective from the definition of AND, probability of A times the probability of defective given A, which is 0.5 times 0.01. So 0.5 times 0.01. Plus, similarly, probability of B and defective is going to be probability of B times the probability of defective given B, probability of being manufactured by B is 30% or 0.3 times the probability of defective is 0.02, 0.02. So it's going to be actually 0.06, right? 0.06, so like 0.06. Similarly, you can do the calculation for probability of C and defective is going to be probability of C times the probability that is defective given that it was made by C. Probability of C making it is 0.2, this 20%, times defective is 3%. 3%, 0.03. Okay, I just made a slight mistake here. 0.3 times 0.02 is 0.006. Okay, it's not just 0.6, 0.006. Okay, so it's 0.006. Okay, so this is 0.006. If I add them all up, I get the probability of defective. Okay, so which is 0.006, 0.006 times 2 plus 0.5 times 0.01 is 0.017. 0.017. So probability of defective is 0.017. If you do the math, it comes out to be 5/17, which is approximately 0.2941 or 29.41%. That is 29.41%. All right. That's the probability that plant A has made it. Now we can do the same thing for plant B and C, right? So probability of plant B making it, given that is defective, which is this one. Okay, probability of B times the probability of defective given B, all of it divided by probability of defective. Probability of defective. All right, so this is pretty straightforward. Probability of B is 0.3 times probability of defective given B is 0.02 divided by 0.017, which is approximately I'm going to just write it out, 6/17. That's approximately 35% approximately. And similarly, you can do the calculation for C, given that D, defective probability of C times probability of defective given C, all of it divided by probability of defective. Probability of defective is 0.017, and probability of C making it 0.2 times defective is 0.03. That also comes out to be 6/17, or approximately 35%. So given these numbers, okay, the probability that A made it is about 29%. Probability that B made the defective product is 35%. And similarly, probability that C made the defective product, 35%. So as a rational quality control manager, you'd probably think maybe either B or C probably has made the defective product, because the probability of A making it is smaller than the other two combined, way smaller. Okay, so that's what it is. Is it clear to everybody?
Yes, thank you.
Yes.
Okay, now let's continue with the materials. Now we are going to do something called fundamental counting rule. Let's go ahead and really do some example. The best way to learn this thing is doing example. Let's say Adam and Bailey, okay, A and B, Adam and Bailey. Adam can dress in two different ways because he has two t-shirts, okay? Let's say he has red t-shirt and a green t-shirt. And Bailey has three t-shirts. She has a blue, pink, and maybe yellow. Adam has two t-shirts colored red and green. Bailey has three t-shirts colored blue, pink, and yellow. In any particular day, they can wear any of these, just one of them. So how many different ways Adam and Bailey can dress up, given that they don't know each other, okay? They're independent of each other. How many different ways they could dress up possibly?
You mean like in a sense, like if you're going red, green, green, red. and
Yeah,
then-
yeah, color
Okay.
combination. Yeah.
So I think Adam has two ways. And then Bailey can do, was it, you said blue, pink, yellow?
Mhm. So you can think of it as this. You have two events. I mean, event A that could happen in two different ways, event B that could happen in three different ways, and they're independent of each other. So together they can happen in 2 times 3, or 6 different ways. And let me show you how it could happen. If Adam wears red, Bailey could wear blue. If Adam wears red, Bailey could wear pink. If Adam wears red, Bailey could wear yellow. Similarly, if Adam wears green, Bailey could wear blue, green, pink, and green, yellow. Do you see there's a total of 6? Now, we can take this idea and expand it to something bigger or more general. Event A and event B, they are independent of each other. That means they don't influence each other. Event A can happen in M different ways. Event B can happen in N different ways. Together, they can happen in M times N or MN different ways. Event A can happen in M ways, event B can happen in N ways. Together, they can happen in M times N different ways. That's called fundamental counting principle. Now, by the way, it does not have to be the case that you restrict yourself to 2 events. What if there is another event? Let's call it C, and that can happen in M and P different ways. Then together, they could happen in M, N, and P different ways, M times N times P different ways. And you can keep going this way as many events as you want. Of course, not infinity probably. All right. So that's the fundamental counting principle. So let's see if there's anything. Okay, I covered this. Then I want to talk about another concept called factorial. Factorial. So first of all, let me define. 0 with an exclamation sign is read 0 factorial is always 1. 1 factorial is also 1. 2 factorial is 2 times 1 is equal to 2. 3 factorial is 3 times 2 times 1 is equal to 6. 4 factorial is 4 times 3 times 2 times 1 is equal to 4. Oops, 24. 5 factorial is 5 times 4 times 3 times 2 times 1 or 120. And you get the idea. In general, n factorial is n times n minus 1 3 times 2 times 1. That's called factorial. In the counting world, this factorial is kind of important. All right. In the counting world, this factorial is important. Now let me give you an example of how to simplify terms involving factorials. Let's consider this. 6 factorial divided by 3 factorial. And please don't do this. 3 goes into 6 twice, so this is 2. That's incorrect. You cannot apply the regular cancellation or addition, or even worse, 6 factorial plus 3 factorial is 9 factorial. You cannot do that, or minus, or regular times. You cannot say 6 factorial times 3 factorial is 18 factorials. Incorrect. How do you simplify factorial? So 6 factorial over 3 factorial. So your traditional operations don't apply here. 6 factorial, I could do the following with it. I could write it as 6 times 5 times 3, sorry. 4 times 4 times 3 times 2 times 1, or I could write it as 3 factorial as 3 times 2 times 1. I could cancel these 3. And the answer should be 120. But we don't normally write it out this way all the way. So what we do, 6 factorial over 3 factorial is 6 factorial is 6 times 5 times 4 times 3 factorial, because this last 3 is 3 factorial. And then in the bottom, you have 3 factorial. Now, this and this cancel out. That gives you 6 times 5 times 4, which is 120. And that is how you simplify factorials. Okay. All right. I think I'm going to stop here for the day. And please go over the Bayes theorem and fundamental counting rule and factorial over the weekend. I may put a new homework assignment, and hopefully you'll get a better understanding of Bayes theorem. And even after watching the video, if you still need help, don't hesitate to ask me. I'm available. I'll be addressing your questions on Bayes theorem on Monday as well. Okay, and we'll probably have a midterm coming up soon within the next couple of weeks or so. Just giving you a heads up. By the 15th of October, we'll probably have a midterm. How does that sound? Is it okay?
Yeah.
Then in about a month, we're going to have another one. Okay, 15th of October, 15th of November, right before Thanksgiving. And then we'll have the final. Okay, any questions from anybody?
No, have a good weekend.
All right, you folks have a wonderful rest of the day, evening, and rest of the week, and have a wonderful weekend. Stay safe, stay healthy, okay? Do social distancing, stay safe, and stay healthy. Take care.
Thank you.
Professor,
Yes.
I actually have a question about the homework.